Let's go on. It's a great pleasure to have Jaime here today. He has a very international background, really, as well. So, traveled from the far distance of Mallorca to Barcelona, Madrid. You've been to Italy, to United Kingdom. A very industrial background as well. Worked for Nokia in the UK, designing 3.5G networks. So everything around designing, optimizing, synthesizing cellular networks, Jaime has seen it all. And today we will see a presentation about a very specific functional block in the architecture which Giuseppe had presented before. Floor's all yours.
All right. Thank you, Misha, and thank you, everybody, for coming this morning after the social yesterday. I'm going to simmer the expectations down a little bit after Misha's introduction. But today we're going to talk about local location management in networks of femtocells, and more specifically in all wireless networks of femtocells, as Giuseppe introduced before. This is a common work between both of us, which has been carried out within the framework of the Femto European project. And, well, this is the agenda for the presentation. You see it's a rather unusual agenda. And because I would like to make it a little bit different, escape a little bit from the formalism of the presentations, and do it the old school way. So what I would really like is that all of us ask ourselves some questions, and we find the answers to these questions together, so that we can grasp a few things about local location management and so on. The first question then would be, what is local location management? Is the thing we're going to discuss today. What is it? The second question would be, why is local location management a challenge in a network of femtocells scenario? And the third question would be, how can we improve the existing 3GPP mechanisms with regards to location management in a network of femtocells? So, you see, 3 questions, no big deal, just 3 questions. So moving on to the first one, what is local location management? I think the best way to explain this is through an example. Mobility management is one of the key components of any cellular network. We've seen today a great presentation by Dionysius about handover management in connected mode. That's the main difference between these two concepts, as I will explain now. Today we're going to talk more about location management, which is a set of procedures that take place in idle mode. The difference is very significant because in connected mode, as most of you may know already, there is a radio and there is an EPC connection between the UE, the user equipment, and the entities in the network. And that's critical because you can send and you can receive information. Whereas in idle mode, there is no such connection. When a UE is in idle mode, it's mute to the network, except from very specific moments in which the UE may report some information to the network. On the other hand, the network is deaf, except for these moments in which the network can listen to the messages that the UE is sending. But this exchange of messages is not as frequent as in connected mode. So the challenges are different, even though some of the common ground is very similar. So as I said, let's move to the example. And I took this figure from the internet. This is a city in the US. If I'm not wrong, this is Seattle. You can see here different macro cells scattered around the urban scenario. You may see some gaps here. I don't really know why they have these gaps, but this is not relevant to the explanation now. And just for a second, imagine a UE moving around this city, a UE in a car, for example. may be engaged in a call, but for the sake of this presentation, let's assume that the UE is just sitting on the dashboard of the car, right? In idle mode. The first thing that comes to my mind when I see a scenario like this is, what happens if someone wants to call you? It's a very basic question, but what happens if your girlfriend, your mom, your friend wants to call you? How does the network find you? How does the network know that you are in this area and not in this area? How the call is routed to your UE? That's what we're going to see now. And that is what we call location management, right? Without the local. Location management in general. How to find the UE in a macro network. But imagine that for whatever reason you want to cover some of these gaps with a deployment of an all wireless network of femtocells, as explained by Giuseppe before. You could have, for example, a network of femtocells here, here, or here, for example. What happens there? The network may know that you are in this network of femtocells, but how do you find someone inside that network of femtocells? Well, let's zoom in and imagine this urban area, and imagine that we have this deployment, right? This figure obviously is not correct, it's not up to scale, but for qualitative purposes, it's good enough. It's more than good. Here you have the proxy MME, as explained by Giuseppe before, which is the entity in the network of femtocells that manages mobility. It's the brother of the MME, but in the network of femtocells, right? And you can have a UE, for example, which is moving around. And as you can see, there are implications in the sense that this guy is moving around, the femtos are smaller than the macros, but we don't shrink the size of cars, we don't shrink the size of humans. So we're going to have, as Dionysius said, more reselections, which is what happens in idle mode, and more handovers, which is what happens in connected mode. So that's an issue that we need to at least take into account and see how we can fix it. So, to the first question, what is local location management? Now we know the answer. The answer is that local location management is the process of finding a UE within the network of femtocells, as opposed to location management, which is exactly the same, but in the macro network, right? So, moving on to the second question. Why is local location management a challenge in network of femtocells? Well, in order to introduce some of the concepts that we're going to use afterwards, let me review a few things that may or may not have discussed these days. I had to skip some of the talks, I'm afraid. So, let's understand how a UE is found in a macro cell, and then in a macro network, and then let's try to port these concepts to the network of femtocells. The location of a UE is known in a macro cell in terms of something called tracking area. And what is a tracking area? Well, a tracking area is basically a group of neighboring cells, right? And that's the type of granularity that you have when you try to find a UE within a macro network. Why do we have groups of cells instead of just cells scattered around, and it would be much easier? Yeah, it would be. But remember, we're in idle mode. The UE is sleeping. And every time the UE needs to report something, it needs to wake up, it needs to connect to the network through the random access channel, it needs to send some information, it needs to receive some information, and it needs to go back to sleep. And that has two implications. First of all, signaling, and the second, battery. And we would like to take care of both at the same time. So, having very small tracking areas in order to have a very fine-grained location mechanism is not an option, because that would drain your battery and that would generate a lot of signaling over the network. So, we group these tracking areas, we group these cells, into tracking areas. And what happens when you have an incoming call? Well, the second main idea here is this word, page or paging, which is the process that takes place when you're about to receive a call. It's the process by which the network sends a message to all the cells in the tracking area where you are registered currently, saying basically, incoming call for user X. All the UEs listen to this, but only user X replies to this message and establishes the connection. So that's paging, which is the counterpart of the tracking area update we will see now, right? That's the process by which a UE is found. And last but not least, we have this tracking area update, which is basically what you can read on the tin. I mean, the UE is moving. Eventually, the UE will change tracking areas. And if that happens, the UE needs to notify the network, I'm changing tracking areas. I'm going from tracking area 1 to tracking area 2. Register me in this tracking area. If someone wants to find me here. And that's the tracking area update. That's what I mentioned before, that basically consists of a process by which the UE wakes up, accesses the network through random access channel, establishes a connection, exchanges some information with the network, basically this message, goes back to sleep. Okay? So that's the tracking area. And these are the two main processes that are involved in location management, paging and tracking area update. So if we go back to Seattle, now you can see, first of all, I have colored some of these cells and grouped them. So this would be a representation, for qualitative purposes again, of what a tracking area is, just a group of neighboring cells. Here you have the path that the UE is going to follow. And that's kind of useful to have it there because these markers here represent the regions where the UE is going to transit from one tracking area to another. So again, if we click play here and the UE starts moving, you see that now every time that there is a tracking area update, the marker goes green. Right? This gives you an idea more or less of this process. Wake up, send messages, go back to sleep. This happens. If these were macro cells, this would happen less frequently. So, a little bit of message sequence charts from 3GPP. This comes from the technical specification 23401, which is basically, it's one of the best ones because you can get most of the details of LTE, both from the EUTRAN site and also from the Evolved Packet Core. So if you want to have like a crash course on 3GPP LTE specifically, go jump into this one. It's quite a good one. Very dense, but there are very interesting sections. And this describes the process that I mentioned before. And I want to insist a little bit. I know this is getting tedious, but this is very important because this is the base of why we want to optimize this. The UE has changed tracking area. The UE wants to send this information to the network. First thing it does, executes the random access procedure. I have simplified the messages here because I don't really want to overwhelm you with all these details. I just want to focus on the really important issues. And here you have the tracking area date request to the HOMINOD-B, which is propagated to, in our case, the proxy MME. Remember, the entity within the network of Femtocells that manages mobility, authentication and security as usual. And this is the message that the UE receives from the proxy MME where the new tracking area is communicated. So now the UE knows that instead of being registered in tracking area 1, he's registered in tracking area 2. And then this optional message in order to complete the procedure. Right? This is a very important message because if you see, this is the only arrow that goes from the proxy MME to the UE, which means that if we need to send any information, that's exactly the place to do it. So let's recap a little bit. We said that we had a problem because we could have a potential high numbers of tracking area updates in networks of femtocells due to the reduced size but same mobility patterns of users. Then this problem could have a very big impact in terms of local location management traffic, and I should add in terms of battery performance in the UE. And this impact is basically posing a challenge at the same time, which is, right, we should design more efficient local location management mechanisms so that we can reduce this over-the-air signaling, which, by the way, is very uncomfortable in all wireless networks of femtocells. So think of a mesh backhaul, okay? And imagine this over-the-air signaling. So we have a problem, this problem has an impact, and the impact is posing a challenge. So going back to the second question of the agenda, we said why local location management was a challenge in network of femtocells. And now we know the answer. So the answer is because when UEs move around, they can generate a lot of local location management traffic. They can drain their batteries as well. And this poses a problem to the network, which may be flooded by this location management signaling. And as I said, there's always the battery issues. So, 2 out of 3. Not bad. Let's go to the third one. How can we improve existing location management mechanisms in a network of femtocell scenario? Well, first of all, what's the main source of local location management traffic? We know that now. Tracking area updates. Second, how can we reduce tracking area updates? You may think, well, let's make the tracking areas bigger, right? Why not? It could be an option. Well, yes, but that also increases the paging traffic. Let's think why. You increase the size of the tracking area, your phone generates less tracking area updates, but at the same time, when you receive that paging message, we said that all the cells in the tracking area are going to be paged. So that's a problem. You get the trade-off, right, between the size of the tracking area and the paging signaling. We have a trade-off here that we should optimize. So ideally, what I would like is something that, in terms of tracking area, is very small for static UEs or semi-static UEs, and is bigger for medium to fast UEs, medium speed to fast UEs. Right? So if you're static, you don't really need to report anything. And if someone wants to find you, and if you're in a very small tracking area, they know where to find you. If you're moving fast and your tracking area is small, you're going to generate tracking area updates constantly. That's not good. If it's bigger, then you have some sort of like a safety environment around where you can move freely, and that's not a problem. So I would like something like that. But of course, I would like this to be dynamic, and I would like this to vary somehow, if possible, with the speed of the UE. But we are in idle mode, and we have no connection with the network. So how can the network know the speed of the UE when the network is deaf and the UE is mute? Well, our solution is something that we call self-organized tracking area lists. And here, I would like to stop briefly and sort of break it down so that we're not haunted by this hocus-pocus expression. And we think about what this means. So first of all, self-organized. Why self-organized? Self-organized in the sense that the UEs somehow are going to report these tracking area updates, and the mechanism is going to be able to vary the size of the tracking area as a function of the speed. And second, self-organized because traditionally tracking areas are A, static, and B, common to all the UEs in the network. We would like something that is defined in a per UE basis. We want individual tracking areas that vary in a function of the speed of the UE. So that's the first part of the hocus pocus word. The second one is tracking area lists. What is this? Well, tracking area lists is a feature that was introduced in 3GPP release 8, so the first LTE release. And it's basically a group of tracking areas. So we said that a tracking area was a group of cells, and a tracking area list is a group of tracking areas, right? And that's very interesting because this is the mechanism by which we're going to group tracking areas in order to allow this variation. We'll see how now. So, if we go back to our example again, and now let's imagine, just for the sake of the example, that each femto in this deployment is a tracking area, right? We know it's not efficient, we know it generates a lot of tracking area updates, but if we want our mechanism to be completely dynamic, we must allow it to vary from the smallest value in this range, which is one cell is a tracking area, to the highest possible depending on the UE speed. So again, if we hit play here and the UE starts moving, you see that every time it enters into a cell, a tracking area update is produced. It could give you an idea of the amount of signaling that you're generating, and it could give you an idea of the battery draining that this is causing at the UE side. In this specific example, 34 tracking area updates. This is the main idea of our mechanism. Remember, individual tracking area lists that vary their size according to the speed of the UE. What happens? We start moving. As we start moving, the UE generates the same tracking area updates as before. But as the UE reaches a certain speed, the tracking areas are bigger. When the UE goes again to very slow speed or even static, you have less tracking area updates. So again, this is the main idea. Now we're going to show all the mathematical background and all that, but if you keep this idea, I'll be very happy for the rest of the weekend. So this is the main thing we should take into account. Fewer tracking area updates than in the previous example, right? Okay, so this is the tracking area update arrival rate as seen from the proxy MME. Remember that entity that manages mobility, right? In the conventional mechanism, we have frequent tracking area updates, okay? Again, this is not up to scale and anything like that. This is just to give you the idea of what are we doing here. By spacing the arrival of the tracking area updates, what we're doing is we're reducing the amount of signaling and we're saving battery in the UE. So that's the key point, right? Right, now what? Now we understand what the idea behind it is, but we should somehow formalize all this and see how it works. And here we go. So, first step. We want to build an analytical model. This has been our approach. We could have run simulations or we could have made it experimentally, but we wanted to tackle the problem first from the analytical point of view in order to characterize this mechanism. So let's build a model that somehow confines all the complexity in some equations. Second, well, let's define a cost function that captures both the paging and the tracking area update contributions in terms of signaling, so that we can somehow formalize this trade-off between these two components. And once we have these two things, well, let's compare both mechanisms, the conventional one and the self-organized one, and see what happens. So the first step when we want to formalize all these into analytical expressions is we need to characterize how the UE is moving, right? Here you have an infinite number of mobility models. We've chosen this one from this reference, which is called a random movement in a 2D topology. It's a very basic, no question about it, very basic mobility model, but we've chosen it for two reasons. First of all, for mathematical tractability. And second, because this is the most random movement you can have, which is a way of saying that we're not exploiting the information contained in the mobility model. Say, I'm a car and I have a UE in my hand, I'm moving this way in a highway, I could take that information into account so that the tracking area list grows in this way, right? I don't want to exploit that information. I want to run all this study in an environment where I have the most random mobility model possibly. And then, if we figure out that cars move in a certain way, or people move in a different certain way, or trains can go backwards, we can exploit all this information. But let's start with something simple and see what happens. How does this model work? Well, here you have what we call rings, right? You see these as a normal femto, and see all these rings here as a tracking area, okay? So we have the first ring here in the center in white, we have the second ring in blue, third ring sort of green, and so on. In each one of these cells, there are two different possibilities. The UE may stay in the cell with probability P, or may escape from the cell from probability 1 minus P. And it has 6 edges through which the UE can escape. That's why the probabilities on each edge. So, also, you can think of P as a knob that you can tune in order to play with the speed of the UE. If P is very high, the probability that the UE is going to stay in the cell is quite high. Therefore, the UE is moving slowly. If you reduce P, the probability that the UE is going to escape from the cell is quite high. And that gives you an idea that the UE is moving fast. So these are the ideas that we need to take into account from this mobility model. What we would like to do with this is to transform it somehow into something we can analyze. And in order to capture the complexity of this mobility model, what we have done is we have defined this discrete time Markov chain. And as you may know, Markov chains are characterized by states, 1 to n, and transitions. States here correspond to what we have called rings, right? This is ring 1, it corresponds to state 1. This is ring 2, which corresponds to state 2, and so on, and so forth. So this is what we have. And these probabilities here correspond to the probabilities of being in this ring and jumping to the second ring, being in this ring and jumping to the third, or going back to the second. All this is captured here. And we do this because we want to calculate what's the probability of having a tracking area update. And as we have explained before, a tracking area update is basically the situation that happens when we are in the last ring and we escape from it, right? When we leave the tracking area. So that's what we want to characterize here. Probability of escaping from a tracking area. Right. By discrete time Markov chain theory, we can calculate that. We just need to solve this Markov chain, assume we are in the last state, and we escape from the last state, right? To the next state, obviously. If we go back to the previous state, we don't escape from the tracking area. Okay, so if we go back to that figure that we presented before, now we see that we have a slotted time axis. Well, that's because we're dealing with discrete time Markov chain, so the time needs to be discretized. And what we have now is these arrows here that represent tracking area updates. Thanks to this mobility model, what we can characterize now is this. Is the probability of having a tracking area update in each one of these time slots. Right. And what do we do now? What do we do now with that? Well, in order to characterize how tracking area lists vary, their size, we have defined a concept that is called, well, that we call stages. And what is a stage? A stage is basically a number that determines how big your tracking area list is. Stage 1 would be this case. That's the UE in static or semi-static mode. As the UE starts moving, then the stage increases, and so does the number of cells in the tracking area. If the UE slows down, it goes back to this state, for example. If the UE stops completely, you go back to this state. If the UE accelerates, then you go this way. So this is the idea, right? Variability of different stages in our mechanism. This figure, I think probably is the most important one in the presentation because it explains how this variability is implemented in the proxy MME, right? So let's break it down a little bit. Here you have the tracking area updates as seen before. So UEs, in this case for a single UE, reporting updates between different tracking areas. And here we have defined two timers, what we call T1 and T2. Well, timers is the everyday mechanism in 3GPP. You have timers that control the changes of states from DCH to fetch and from fetch to idle. You have timers that control handovers, as Dionysius explained before. You have timers that control the periodic tracking area updates, timers for everything. So these are timers in the proxy MME. T1 is going to control how fast these stages grow, whereas T2 is going to control how fast they shrink and for how long they stay in the same size. These are the main three events that you can have in this mechanism. If the tracking area update arrives before T1 has expired, you could see that as the UE moving too fast for its current tracking area size. So the outcome of this action is go to the next stage, grow, in other words. The second event that we could have is a tracking area update that arrives once T1 has expired, but before T2 expires. And that means that the UE feels comfortable, somehow, with the size of its current tracking area list. Third event is a tracking area update that comes after T2 has expired, which means, right, this tracking area list may be too big for the UE. We can go back to the previous stage. So this is how we control the mechanism. So to a certain extent, this is a mechanism that does not impact on current 3GPP specs because you're using standard messages and allows you to estimate roughly the speed of the UE at the proxy MME. And as the proxy MME is the entity that sends the information to the UE about the new tracking area lists and which cells are included in the tracking areas, we have a mechanism by which the MME can send this information, and we have a mechanism by which the MME can estimate the speed of the UE. So again, this is the idea. How do we characterize this? Well, go back to the discrete type Markov chain concept. We define a new one where here we have these stages now. Remember, these stages is grow and shrink. These are the states here. And the transitions are basically the probability of changing from stage 1 to stage 2, going back to stage 1, going to stage 3, and so on. From this discrete time Markov chain that somehow captures the complexity of the self-organized tracking area list mechanism, we extract the state distribution probabilities. And now we can say that, for example, for stage 2, we know what the probability is. And therefore, we can characterize all this complexity in terms of numbers, which is what we want, because that's going to be what we're going to feed into our cost function in order to see how well it performs. So, we said that one of the steps that we wanted to cover was the analytical model, and another one was the definition of a cost function that captures both the paging contribution and the tracking area update contribution. This is the cost function that we have come up with. You could come up with much better ones probably, but this is ours. Basically, it captures the contribution from paging and the contribution from tracking area update. This is the probability of having a paging, that means of receiving a call in a specific time slot. This is the average number of cells that are going to be affected if this paging comes. And this is the cost of a single paging operation, so no big deal. And this is the probability of having a tracking area update, and this is the cost of a tracking area update. Now, we said before that the tracking area update was a very expensive or a very painful procedure in terms of signaling and battery. And that's what we capture here with this signaling ratio, right? What we want to do is we want to normalize all this expression by dividing it by the cost of a single paging operation. This is difficult to estimate, but in the literature, they assume that this alpha parameter is more or less around a value of 10. So a single tracking area update operation is 10 times more expensive in terms of signaling than a paging operation. Right, so we have the cost function, and then let's see what happens. So we can evaluate this cost function, which is what we have here, the normalized cost function, for different values of P, which, if you remember, was that knob that we had in order to vary the speed of the UE. So see this axis as speed if you want, okay? And this axis as the cost. This value here is basically the paging arrival rate, which is how often your mom is calling you, right? Normally it's expressed in pagings per hour. So in this case, your mom doesn't care much about you. And normally it varies between 0.1 pagings per hour to 10 pagings per hour, which would be a mother that is calling you every 6 minutes to check where you are and why you're not at home. And these are the two mechanisms. Here we see the static one, and here we see the dynamic one. And as you can see, there's no black magic here, because the mechanism is very simple. Sometimes it behaves better, sometimes it doesn't. And this arrow here indicates what we have called the activation point. Why? Because we may not want our mechanism to be dynamic all the time. We can activate it whenever it starts being, whenever it starts improving the performance in terms of the paging and tracking area update costs. So, if you think about the UE changing its speed, you could think about using the static mechanism until the activation point is reached. Once the activation point is reached, then you start with the static mechanism. And if the UE decreases its speed up to this point, then we go back to the static. So here what we try to do is we try to capture the best of both worlds, right? There's no silver bullet. The most sensible solution is to use both at the same time. Here we have the same figures, but for different values of paging arrival rates, right? From 0.1 to 10. And again, see these as speed and these as cost, right? And you can see that you have different shapes for different points here, for different values of lambda sub p. The main idea behind this is that if we evaluate the savings that we get with these performances, the numbers that you get are more or less in this order. For the first case, a very low paging rate, you can achieve up to a 39% less signaling traffic than with the static mechanism. In this case, we achieved a 33%, and then as you can see, the savings are reduced up to this point where you get a 4%. So, back to the agenda. The third question was, how can we improve existing 3GPP location management mechanisms in a network of femtocells? And the answer is, well, we can by creating individual tracking area lists, as opposed to the static and global ones, that can vary their size according to the speed of the UE. That's the answer to the third question. Coming up to the end of the presentation, what are the main conclusions here? Well, I think there's little to be said, actually. I think the conclusions of this talk are the three answers to the questions. First of all, what location management is, more specifically, local location management. Second, why local location management is a challenge in a network of femtocells. And third, how can we improve local location management mechanisms. So if you want to know the nitty-gritty of all this presentation here, you can take a look at this paper, which is available at this website, which is my personal website at CTTC. You can download a approved version by signing a very nice IEEE contract. And you can take a look at it. So that's all from me. If any of this has been of your interest, I would like to thank you very much for your attention, and now the stage is yours.
Excellent. Thanks, Herman. Any questions? Yes, wait.
Thank you for your presentation, and I have one question. So you believe this was only for the sparse deployment?
What do you mean by sparse deployment?
I mean, sorry, for the dense deployment of femtocells.
Yes, that's
so
the...
my question is, how do you calculate the stages when there is a very sparse environment, deployment of femtocells?
Okay. No, we haven't, because the scenario that we're considering in bFemto is a network of femtocells, actually an all-wireless network of femtocells deployed in a dense urbanist area. So this is the, let's say, the starting point for all our study. It may be very interesting, and it is actually very interesting to consider sparse scenarios and what happens if you have, instead of a wireless link, a wired link, for example, and things like that. But just for the sake of simplicity and in order to focus our work, we've dealt with the dense urban scenario.
Okay, thanks.
My pleasure.
Thank you. Thank you very much for your nice presentation. My question was regarding the deployment layout that you have used. Did you use this conventional two-tier model for, modeling everything? And if so, what would be the differences if you try to use something like a 5x5 grid model or other 3GPP models, which are more, I think, into the framework of femtocells rather than the conventional model?
Okay, so you're talking about how the femtos are scattered around the city.
Yes.
So instead of using stripe models and things like that, or?
Yeah. In this model, your model, is it based on the conventional two-tier interference, or is it, for example, based on 5x5 grid?
We don't deal with interference here at all. I think.
Yeah, I know. But I'm talking about the layout.
I know. Well, I assume that you could deploy femtos in different frequencies and, for example, have users who don't really require a good quality of service, have them connected to the macro, and then if they need some special quality of service for any reason, then they could go to the to the femto frequency, as you have, for example, in hierarchical cell structure. But we have not really come into these details. We just think of a network of femtocells. That's a decision that belongs to the network operator.
Thank you.
Any other question? I have a more maybe philosophical market question. IEEE Wi-Fi got away without any mobility management whatsoever. Users are content, just come home, do it manually. They know they come home, there's a Wi-Fi station. It just worked.
Yeah.
And so the big question is do we all need it? Is that maybe the value proposition which will really differentiate it with respect to Wi-Fi and maybe facilitate a real takeoff of femtos? How do you see that?
You mean the deployment of network of femtos?
Yes.
If that's a real alternative to
right.
Wi-Fi.
No, the whole issue of mobility management, handovers, vertical, whatever. It goes a little bit beyond.
I see
what you present.
mean.
Yeah.
Well, first, truth be told, I think that, as you mentioned in your talk, I think that the main difference between Wi-Fi and cellular networks is obviously the possibility of performing handovers, keeping your connectivity through your moving. I'm very happy with my Wi-Fi access point, but as I leave my house in the morning and I'm checking my Twitter, it takes a while until it connects to the 3G cell, and then I can continue. And if I'm browsing, I really notice it. So deployments like this, I think that as we are moving from a paradigm of coverage to a paradigm of capacity, we're going to have to deal with many more technologies at the same time. So somehow we are going to have to integrate all of them in order to make the best of them at each circumstance. Deployments like this, for example, dense urban scenarios, make sense, for example, for very specific regions which may have some coverage problems, such as areas of the city with big buildings, things like that. Campuses like this, big enterprise, maybe. But I think that the main advantage over Wi-Fi, as I said before, is just the seamless handover. Whenever a seamless vertical handover is implemented, then we will be able to benefit from Wi-Fi. And from a user point of view, I think that's what I really request from my network operator. So if this, which is owned by the network operator, can somehow guarantee that my quality of service is going to be up to the levels that I expect, and the handovers are guaranteed, then it works for me as a user. I'm happy with it.
Okay. Thank you. Excellent. Very good.
Thank you.
Then thank you very much.